Okay, so in this video, we will talk about something called Thevenin's theorem. In my opinion, this is probably the most powerful technique in electrical circuits. Okay, so what does it say? So let me give you some context. So maybe you have this circuit and we are told to calculate the current through this 2 ampere 2 ohm resistance. Okay, so you have to calculate the current through this resistor. Now, yeah, you can do this. Maybe you use nodal analysis. So you have node 1 here, node 2 here, node 3 here, and then you use Ohm's law to calculate the current. Okay, yes, you can do that. Now, what Thevenin's theorem does is it actually simplifies the problem a lot. And the way it does is actually using the power of equivalent circuit. So there is one more thing I want to talk about. So yes, you can calculate the current this way using nodal analysis. But then I might ask you, okay, so what if I change this resistance to 3 ohm now? The current will change, but what will be the current? So to calculate that, you have to go through the whole nodal analysis process again and then figure out what the new current is, right? Or maybe then I say, okay, after you have calculated 3 ohm, then I ask you, okay, what about 4 ohm? So then you have to do the same thing again and get the result. And maybe in general, I can actually ask you any current, right? So maybe I ask you, okay, if I have a resistance called RL, L for load, this is just a common term we use. So if I say, okay, so for resistance RL, what will be the current through this? And that you can calculate that, but it will be a little painful because every time I change the resistance, you have to calculate the whole thing again. So what Thevenin's theorem does is that you have this huge circuit, and using the power of equivalent circuits, what it does is Thevenin's theorem says the whole thing, the whole large circuit has an equivalent circuit, and that is just simply a voltage source and a resistance and nothing else. So any large circuit you can imagine, whatever circuit you can imagine with of course just a voltage source, resistance, then dependent source, current source, etc. With these elements we have already seen. Any large circuit with this huge complexity, you can actually convert them just one voltage source and one resistor. Okay, so this is equivalent to the whole thing in this green box is, well, this is not any box anymore, but the whole thing in this box is equivalent to just this one voltage source and resistor. Okay, so now everything outside the box we just change everything inside the box, and everything outside the box remains the same, right? From the equivalent circuit video, you should know that. So now it's much easier to calculate the current because the circuit is way simpler now. Okay, well, of course we have to know the values of the voltage source and resistance. We don't know what the values are yet, but if we know them, so let's say for example this voltage source is 30 volt and this resistance is 4 ohm, you can easily calculate what current is going through that resistor, right? So if I say, okay, so if I have had 2 ohm here, and I ask you, okay, what's the value of the current? So you just go, okay, so the whole thing is equivalent to 3 volt and 4 ohm, right? It is equivalent to 3 volt and 4 ohm, and 4 ohm. And now I have this 2 ohm resistor, And so then the circuit is very simple. You have 4 ohm, 2 ohm, they are in series, you just add them up, 6 ohm, and you calculate the current to be 5 ampere, right? So this is very easy once you have the circuit. And if I change the values, okay, so what about 4 ohm? So you can go, okay, yes, all right. So if you ask me about 4 ohm, so now it's 4 plus 4, 8 ohm, and you can calculate the current again. This is very simple because the circuit is very simple now. And we can go even farther than this. So I can say, okay, I don't want resistors here. Okay, so I want, maybe if I put a voltage source here, let's say 20 volt voltage source, what will be the current in this direction, right? Okay, let me draw it properly. So you might be interested in this current. And yes, of course we can do that. We can just keep changing this to whatever our circuit demands. So we can have 20 volt voltage source here, and yes, of course we can calculate this simple current. This is a very simple circuit, right? So anything you ask about this circuit, I can answer them via this circuit, because this circuit, okay, so you have to change it here. I'm just drawing it here, so forget that. So any question I ask about this circuit, this huge circuit, you can answer them using its equivalent circuit, which is very simple. And that's what it means to be equivalent, right? Anything you ask about the main circuit, you can circuit A, and you can answer it using circuit B, its equivalent part, right? And so you can think of it like a generalization for all equivalent circuits, right? So we have seen source transformation just works on a voltage source with a resistance in series. But here, Thevenin's theorem is a really more general approach for any circuit. You can convert them into this equivalent circuit. But the problem lies here that we don't know these values. Once we know these values, it's really easy to calculate. So what we like to call them is Thevenin's voltage and Thevenin's resistance. Okay, so V Thevenin and R Thevenin. This is the notation we use. Okay, so we have to figure out the values of V Thevenin and R Thevenin. And once we do that, any question you ask about the main circuit can be answered using this simple circuit. Okay, so how do we do that? Well, there is something I want to, okay, so I can give you the procedure, but I want to just give you some justification for that. Okay, so if I had, okay, so maybe I had open circuit here. So I ask you, okay, so I keep this open, so there is no current, but there can be voltage, right? So here I keep them open as well, and there is no current, right? There is no current. No current in both cases. They are equivalent, so there will be no current in both cases, but there is a voltage, right? So if you take this circuit and say this is a voltage. If you remember our lecture from 250 lecture from that wire, you should remember that even though you have open circuit, you don't have current, but you have voltage. And for short circuit, you don't have voltage difference, but you have current. Okay, so it's kind of the opposite of each other. So you will have a voltage, and you can actually calculate that voltage as well. So if you take this as ground, and you have a voltage node here, a node there, V2, let's call it V2, and this is V3. So VOC will just be V3 minus 0, right? Positive terminal minus negative terminal, so which is just V3. And you can actually solve this using just nodal analysis. Okay, so you know the value of VC. So maybe you have some value. Okay, so let's say 30 volts, we get it. Okay, and look at this circuit. Well, you will also have some voltage here, but exactly what voltage? Well, you will have VOC here as well because they are equivalent. But what's nice that since you don't have a current here, so there is no current here, right? That means, okay, so let's take this as ground. This is this node's voltage is V Thevenin, and this node, well, I can't call it VOC, right? The difference, or maybe you want to call it V1, I don't know. So if we had a current I, we would say V Thevenin minus V1 equals to 0, or why am I saying 0? So if there was a current, we would say I times R Thevenin, just using Ohm's law. But our current here is 0, right? So this current is 0. So we have just 0 times something is 0. And we have V Thevenin is equals to V1, which is just VOC, right? So which is just VOC. So basically, you have, if you have no current, you get the full voltage. Okay, so we already know the value of VOC though, right? We can actually calculate the open circuit. Okay, OC stands for open circuit, right? I forgot to mention open circuit, OC. So we know the value of open circuit voltage using nodal analysis. So this is 30 volt nodal, the open circuit voltage is 30 volts. So you know that V Thevenin is 30 volts. So you already know the value of one thing. So this is 30 volts. All right. And I will show the whole example later. Don't worry. Now, what else can we do? So how do we figure out the R Thevenin? How can I do that? Well, this time we use short circuit. Okay. So if instead of opening the terminals, if we had shortened them, so if we have shortened them, well, we wouldn't have any voltage difference because there is no voltage difference between a continuous piece of wires. So that would be just 0. But there is some current, right? Some current will go from here to there, right? So, and that current, we call it I short circuit, ISC, short circuit current. And again, you can calculate that because that's the current going through this side, I short circuit, and that those electrons are going to move in like this. So that current is going through this wire. So we can figure out I short circuit just using nodal analysis and then using Ohm's law on this 1 ohm resistor. We will figure out the short circuit current. And then once we do figure out the short circuit current, okay, so we have to do the same thing here as well, right? So if we have the short circuit here as well, if we had the short circuit here as well, we would have a current, right? And the same exact current, I short circuit current, because they are equivalent, right? Everything outside the box, the short circuit current is going outside the box, so they will be exactly same. And look, what will be the value of short circuit current? Well, the node here is just ground, so this here is 0 volt, and this is here is 30 volts, right? Or you can say, well, if we didn't know the value, let's just say V Thevenin or VOC, whatever you want to call, they are equal. Okay, so then I short circuit will be VOC, or open circuit voltage, minus 0 volt, or 0 volt divided by R Thevenin, right? And we know that then okay, so you are just minus 0, you can remove the minus 0 part, nothing's gonna change, and now you have R Thevenin equals VOC divided by ISC, right? So you know the value of ISC from using short circuited current, and you know the open circuited voltage from opening the circuit. Okay, so when we use the open circuit, so our goal here would be to, so when we have a circuit, so like when we had this, so originally we had this circuit, right? Well, we didn't have it shorted, so maybe there was a resistance called RL, and we were to figure out the current I. So our first step will be, step 1 for Thevenin's theorem will be to replace RL with open circuit. So okay, so let's replace RL with open circuit. Okay, so we will just open that. So we have this circuit. So whatever we find after we opening, we use nodal analysis. So step 2 will be nodal analysis on open circuit, nodal analysis on that open circuit. And after doing that, the open circuit voltage you will find is your Thevenin's voltage. So this is already one of your answer. Okay, so one of your answer. Okay, now what else? Then we move on to the short circuit current. Okay, so the short circuit current, we will do the replacing the RL with short circuit. Okay, and then step 4, we do nodal analysis, or any technique. Basically you can do the source transformation if you want on the short circuit version. Then you have you find out the current ISC, right? Once you have found out the ISC current, you will find R Thevenin quite easily, that VOC divided by ISC. So you figure out the VOC from the previous step 2. So after doing step 2, you will find out the value of VOC and then use it to VThevenin R Thevenin, calculate the values of VThevenin R Thevenin. Once you found the values of VThevenin and R Thevenin, you basically know everything there is to know about that circuit. All right, so now your circuit will be just VThevenin and R Thevenin. Okay, so anything you want, you can put it here, and any question you want to answer about the main circuit, you can do it here. Okay, so we wanted to ask what will be the value of value of current if we had RL. So we put here RL and figure out the current. Okay, so let's do this exact example in procedurally. Okay, in the next video.